Hi everybody. So this next section, 1.3, is a review of trig functions. Um, so hopefully you've had trig in the recent past, but we are going to review some of these. I should mention too that if you do need more review on the college algebra material, I do have several videos related to college algebra on my YouTube site if you're interested in going over those. Certainly not required to, but certainly can if you want. So let's just kind of quickly review the trig functions and maybe go over some problems here. So remember that there's several different ways to measure angles. You can measure them in degrees, but remember radian measure is also another way you can do that. And the radian measure of a central angle in other words, with the center of the angle at the center of the circle, or the vertex of the angle at the center of the circle, is this number theta, where you're basically taking the arc length divided by the radius. So you're basically, the radian measure will basically tell you how many radiuses there are that subtend this angle. So just think of it that way, right? If somebody says like 2 radians, that means you can wrap 2 radiuses around the angle that you're referring to. And so that gives us the arc length formula. So remember the formula for the arc length, right? The length of some arc S. It's determined by the radius of the circle and then the size of the angle. Just remember that theta has to be in radians if you're doing that, right? So basically you're just taking, the radius times the number of radiuses, and that gives you the arc length. Remember, the arc length is measured in inches because it's a length. Maybe just to review some angles and how they convert to radians and degrees, right? So remember, there's 180 degrees equals pi radians. Right, so that means halfway around the circle, you can wrap a little bit more than 3 radiuses around the outside of the circle. And remember, I guess radian measure is sort of length independent in the sense that it's measured in terms of the radius, whatever the size happens to be. But so these are just some conversions, right? And so remember, to convert, like let's say you wanted to convert 30 degrees to radians, right? Remember, you basically just multiply by this conversion factor, right? You have 180 divided by pi. 30 goes into 186 times, so that'll give you pi over 6. So that's one way to convert. And then remember, if you need to convert back, you can just do the reverse, right? So if you need to convert pi over 3 radians to degrees, right? So for every 180 degrees, you'd have pi radians, so you could just multiply by that, and that would give you the angle measure if you forget. But again, you might want to have these memorized. I'll probably let you use a formula sheet on the midterm and the final, so I don't know if you have to have these memorized, but hopefully you're familiar with these already, but I would maybe at least copy this down on your formula sheet. So remember that as far as measuring angles, an angle is in standard position if its initial side is on the x-axis, and then remember, angle measure is positive if you're rotating in a counterclockwise direction, and then it's negative if you're moving in a clockwise direction. Remember also that you can have several different degree measures that will wind up at the same spot. So for example, you could go around pi fourths, but if you go around 9 pi fourths, right, that will also land you at the same spot. And remember, angle measures can be 0, or it can be negative, and you can go around the circle more than once. These are the definitions of your trig functions. Again, hopefully you've seen these before, but again, you might want to copy these down on your formula sheet. And remember, these are only good for right triangles. So if you have a right triangle here and an angle here, this is the side opposite the angle, this is the side adjacent to the angle, and remember the hypotenuse is always the side opposite the right angle, right? The trig functions are defined in this way. And remember that these are reciprocals of these. So cosecant is the reciprocal of sine, secant theta is the reciprocal of cosine, cotangent theta is the inverse of tangent. And don't confuse these with the inverse trig functions, right? So that, remember, the trig functions take angles to ratios of sides. The inverse trig functions, for example, would take a ratio of sides, some number, and you would output some sort of angle, right, either in degrees or radians. We'll talk about those a little bit later. But so if you have a circle of radius r, you can define the trig functions, if you think of this as your angle theta, in terms of the length of r and x and y, where this would be the hypotenuse, and then this would be the adjacent side, at least to this angle, and then that would be the be the opposite side of this angle, and this would be the adjacent side, right? This side and this side will have the same length. Here are some common triangles that you will encounter in trigonometry. Again, I would encourage you to have these memorized. But if you have again, both these triangles should have 90 degrees, but if you have a 45-45 triangle, remember the length of the hypotenuse is the square root of 2, and then the two legs are 1 and 1. If you have a 60-90-30 triangle, remember this is 30 degrees and this would be 90 degrees. The ratios of the sides are given by that, right? The hypotenuse is of length 2, the side opposite the 60-degree angle is square root of 3, and the side opposite the 30-degree angle is 1. Another thing to remember is that the trig functions will be positive or negative depending on the quadrant that you're in. There are several mnemonic devices for remembering this, like all students take cash or all students take calculus or something like that. But remember, all the trig functions are positive if the angle is between 0 and 90 or between 0 and pi halves. In this quadrant here, right, only sine and its reciprocal cosecant is positive. Here only tangent and its reciprocal tangent is positive, and here only cosine and secant are positive. Here's another mnemonic device also is calculus activates students' thinking. I guess I never heard that one before. But so whatever you need to do to help you remember that, and again, you can certainly copy that down on your formula sheet. So remember that if you're in some quadrant other than the first quadrant, right, you have to sort of use this auxiliary or helper angle here to help you figure this out. But remember, in particular, right, if you're in the second quadrant, right, sine would be positive, cosine would be positive, and sine would be, cosine would be negative, the adjacent side would be negative, and this would be positive. Right. Here's some values of various of the sine, cosine, and tangent. And remember, you can get the other ones by just flipping these upside down, right? So if you wanted, say, cosecant of negative 135, right, that would just be negative 2 over the square root of 2, etc. You might have to rationalize the denominator. But again, this is another formula sheet, or that you might want to put on your formula sheet, is this table if you don't already have it memorized. You should be able to kind of construct all that from these two triangles, but that's, it takes a while to do that. So, I would just copy that down just to be on the safe side. If you want to go back to scratch to these two triangles to generate everything in this, you certainly can do that. So let's look at an example here. So let's say that we know that cosine of x is equal to negative 5 over 13. And it's in the angle here, x, is in between pi halves and pi, right? So what quadrant would that put that in, right? Well, that would put that in the second quadrant, somewhere over here, right? Because here's pi halves, pi would be 180 degrees. So it's over here. And so if you draw your triangle here, right, I guess you could think of this as being like the length of the adjacent side, which is 5, because you're dealing with cosine, over the hypotenuse, right? So you could think of this length as 5 and this is 13, and because you're in the second quadrant, again, remember the only thing that's positive in the second quadrant is sine or cosine. So that'll help you maybe figure out the other sides. Again, we know this is a right triangle, so if this is of length 5 and this is of length 13, and we want to be able to figure out what this side is, right, we've got y squared plus 5 squared is equal to 13 squared. So you've got y squared plus 25 is equal to 169. So y squared, if you subtract 25 from that, will give you what? 144. That means y, this length y has to be 12, right? So you should be able to get all the other trig functions from that. Here's the solution on the other side, right? So we've got this triangle here in the second quadrant where this length is 5, this is 12, and this is 13. Here's your right triangle. So remember, sine then would be the opposite from the, I guess we're technically talking about this angle, but if we're talking about the reference or helper angle, you'd want to do it with this one. Or it'd be the side opposite of that angle divided by the hypotenuse, which is 13. And again, sine should be positive in that quadrant. Tangent will be negative, right, because you're taking basically a positive 12 divided by negative 5. Secant will just be negative 13 over 5. And then cosecant, again, that's just going to be the reciprocal of sine, so that'll be 13 over 12. Cotangent, again, will just be the reciprocal of tangent. Now remember that the trig functions are periodic in the sense that their pattern repeats, they're cyclical, right? And so most of the trig functions will have a period of 2 pi, meaning that if you shift the graph by a period of 2 pi, it'll land back on itself. But remember, tangent and cotangent do not have that. We'll look at the graphs of these functions in just a little bit to remind you of that. But these are some trig identities you might want to put down on your formula sheet. And so, in general, there are other periodic functions besides the trig functions, but a function is periodic if you can add or subtract a number p and it gives you the same function back, just like these. So in this particular case, p would be pi. Here, p would be 2 pi. So here's the graph of some of the trig functions, right? Here's the graph of cosine. Remember, cosine's an even function, so it should be symmetric about the y-axis here. Here's sine, tangent, secant, cosecant, cotangent. So again, you might want to put those down on your formula sheet also. And one thing to notice here too is you can kind of get the reciprocals of these. Like if you were to draw, cosine here, the cosine curve, and then sort of turn it inside out. Imagine you sort of flip this part up and flip these two parts down, right? You'd get the graph of its reciprocal. Same thing here if you take the graph of sine and you flip it upside down. That might help you remember what these look like, but again, you'll have a formula sheet. A couple of other identities. Remember, like I said, cosine is even, so that means if you replace the x with negative x, you should get the same function back. Same thing with secant. And then sine, tangent, cosecant, and cotangent are odd. And basically what that means, remember, function is odd is if you can take the negative outside of the function. Here's some other well-known trigonometric identities that you should put on your formula sheet. We will be using these a fair amount later on, so make sure you're at least familiar with these. Try to memorize these if you can, but again, I will put them on your formula sheet, maybe just to talk about these. This is known as the Pythagorean theorem, right, because you're basically taking x squared plus y squared is equal to 1. These are other Pythagorean theorems involving the other trig functions. These are what you get if you want to take the cosine of two angles added together. You might assume, well, I can just take the cosine of the first thing plus cosine of the second thing, but it doesn't quite work that way, right? You've got this identity, and then here's a similar one with sine. And so make sure you're familiar with those. As far as the double angle formulas, you've got cosine of 2 theta, and these identities can be gotten from these by just replacing a and b both with theta. So if you have cosine of theta plus theta, that gives you 2 theta. So you can always derive these if you really want to. These are kind of hard to derive. You have to do it geometrically, but once you've gotten a lot of these identities, you can base it on ones that you already know. Here's sine of 2 theta. Remember, that's 2 sine theta cosine theta. Cosine squared theta is equal to this. Sine squared theta is equal to this, right? The only difference is here you've got a plus for the cosine and a minus for the sine. And then here's the law of cosines, or at least one form. And remember that if the angle theta is 0, you just get the Pythagorean theorem. So So just remember the law of cosines, again, can be used for non-right triangles. Just remember that the side C has to be opposite angle C, and side little b has to be side opposite angle b, etc. So you might remember, just like other functions, trig functions can have transformations applied to them. So remember that adding or subtracting a number on the outside of the function will shift the graph up or down. Adding or subtracting a number inside the argument of the function will shift it left and right. This will compress the graph horizontally, or will reflect it around the y-axis if b is negative. And then a will have, that sort of affects the amplitude, or how high up or down the graph will go, or the vertical stretching or compressing. And remember, if a is negative, that'll flip the graph upside down around the x-y axis. So when you're doing transformations, a lot of times you can do them in any order that you want, but you do have to be a little bit careful of this. So you should try to do these things in this order. You should try to do horizontal translation caused by h. And I know I relabeled these from the last slide here, right? So in the last slide I called HC, here I'm calling it H. So you want to do the horizontal translation, and then the horizontal shrinking or stretching caused by B. Finally, vertical shrinking or stretching caused by A, and then lastly add the vertical shift. So here's an example. This one's pretty easy. Right, so this is just going to take the graph of cosine and shift it. Remember that you take the opposite of the sign, it'll shift it 2 pi thirds to the left, and then it will shift it down by 2. Remember, you might have seen the formula for calculating the period. Now remember, for tangent and cotangent, right, the period is just pi over b. But for all the other trig functions, it's 2 pi divided by b, where b is the number that's in front of the x. And if there is a number here, you should really factor it out of each term inside the argument, but in this case you don't have to do that. So you're just taking 2 pi divided by b, so there's no change in the period, so there's no stretching or compressing this way. But there is a phase of negative pi over 3, so phase just means you're shifting the graph left or right. So you would shift the graph again to the left by 2 pi thirds. So imagine you take the graph of cosine, which normally looks like this, and you shift it to the left by 2 pi thirds, and then the negative 2 again will move it down. You'll get a graph that looks something like that. A couple of other identities to remember is that sine of theta is always between the positive and negative of whatever the angle is, right? So sine of theta is always smaller than the angle. And then 1 minus cosine theta is always between theta and, or negative absolute value of theta and theta. You can kind of see that from the figure here. You can also derive another identity here, which is that sine squared theta plus 1 minus cosine theta squared is less than or equal to theta squared. So I guess, basically if you take the sine this distance here and square it, and then take 1 minus cosine theta squared, which is given by this, right? So I guess you'd have a square here that's this wide and that wide that way, and then a square that's this wide and that wide that way. It should be less than the area inside the wedge squared, right? So I guess the area here, right, should be smaller than the area inside the wedge. So remember, theta is the angle measure here, I guess. So one thing that we're going to do then is use some of these formulas to derive certain identities. And so, there's really nothing to solve here, right? The idea basically is you want to start with this identity, and by a series of substitutions arrive at this identity, or vice versa, right? You want to start with this and work that way. And so in this particular case, it does say to use the addition formulas in the solution here. Now, I suppose there might be other ways to do this. You could maybe use the phase shift formula or transformation formula here. But let's go back to our addition formulas, primarily for sine, and see if we can use that. So we'd want to use this formula, and you can think of b itself as being negative. So in this case, you could think of x as being like the a, and then negative pi over 2 as being like the b. So you could really write this as sine of x plus negative pi over 2, and we want to show that that's equal to negative cosine of x. And I suppose there is a way to sort of think about this graphically also, right? You're sort of taking the graph of sine and you're shifting it pi over halves to the right, right? You're shifting it this way, pi over halves. It should look like the graph of cosine flipped upside down. But we really want to do these algebraically, but you can sort of think of them sort of more geometrically. So just substituting into that formula again, where a is x and b is negative pi over 2, you would get this identity here, right? So plugging into that formula, right, it should be sine of a cosine of b minus cosine of a sine of b. Well, luckily a lot of these sort of disappear, right? Cosine of pi halves, that's just 0. So that means this whole term is going to disappear. So we really only have to deal with this, right? Sine of pi halves is just 1. And so you just get negative cosine of x times 1. Well, that's just negative cosine of x, and then we've proven what we've needed to prove, right? We want to show that you can get from here to here, right? This is not an equation, so you don't want to solve it for x, right? It's just an identity. Now, they won't always be this easy. Some will be trickier than others, but I'll try to give you some that's reasonably easy on the exam. Here's another example. Let's say that you want to express the given quantity in terms of sine of x and cosine of x. So again, probably want to use the same identity we did before, right? So it'd be sine of a times cosine of b. And I maybe should have had a... I guess I should have maybe had negatives in here. Either that or I'm using a different identity here. And so then you'll have cosine of x minus cosine of pi halves sine of x. Well, again, this is 1. This is 0, so that disappears, and it gives you negative sine of x. And so the directions here might be kind of silly, right, because they say to write the answer in terms of sine of x and cosine of x. Right? I think they mean and or, right? So I guess there is a cosine of x in there, but it's being multiplied by 0. So, so if you get the answer in terms of sine of x, that's good enough. But if you have questions about what the directions mean or what I'm asking you to do, especially on an exam, don't be afraid to ask, because sometimes what I think is perfectly clear may not be as clear as I think to you guys. So here's another example. So here's an example where we're not proving an identity. We're trying to solve a trigonometric equation, right? We're trying to find all the angles theta that we can put in here that are between 0 and 2 pi. So in other words, between 0 and 360 degrees. So if I take cosine of 2 times the angle plus cosine of the angle, I get 0. Right, so this will be true for some values of theta and not other values of theta, unlike a trigonometric identity, which is true for every value of x. So again, how would you go about tackling something like this? Well, again, there might be more than one way to do it. We could use the double angle formula, right? Remember, we had cosine of 2 theta was equal to 2 cosine theta squared minus 1 plus cosine theta. And these can get to be kind of tricky. So you might have to play around with some of these a little bit. But if you get stuck, just let me know. And then I guess if you look at it, I guess there's a couple ways you could look at this. If you think of cosine of theta as being kind of like an x, this is really just the... you could write this in terms of the Pythagorean theorem, right? So here's the identity we're using for cosine 2 theta, right? You can actually rewrite this identity in terms of cosine squared theta. And then remember, about the Pythagorean identity, you can write this as 1 minus cosine squared theta. And so if you simplify that, you do get 2 cosine squared theta minus 1. But my advice would be, when you're trying to solve something like this, try to write everything in terms of one trig function, like everything in terms of sine and cosine, and then you can factor this, right? So if you think of this as sort of like solving 2x squared minus 1 plus x is equal to 0, you can either factor that or put it into the quadratic formula. In this case, I'm just going to factor it into like 2 times x minus 1 plus x plus 1, except instead of x, I have cosine theta. And so then if you're multiplying two things together and you get 0, either this has to be 0 or this has to be 0. So that means that 2 cosine theta minus 1 has to be 0, or, right, cosine theta plus 1 is 0. Well, if I move the 1 over and divide by 2, I get cosine theta is equal to 1/2. Well, think about what are the angles between 0 and 360 that will give you a value of cosine of positive 1/2, right? And so that would be like 60 degrees and 300 degrees. And here you're asking what values of theta would give you cosine is equal to -1. Well, there's only one for that. Right, that's 180 degrees. And you can write your answer in terms of radians or degrees. It doesn't matter, but just make sure that if you're doing degrees, put the degree symbol on there, because if you don't write anything down, I'll assume that it's radians, right? So either, so in this case, the answer would be 60, 300, and 180, or pi has 5 pi thirds and pi. And again, you could, I guess, graph the function and look and see where the height of the function is 0 between 0 and 2 pi, right? There should be 3 spots there. This got kind of cut off here. This should be pi thirds here. Okay, so hopefully that gives you guys an idea of what to do with this section. If you guys have questions about anything else or whatever, just let me know.